Yo, physics students. Oh, here. Yo, physics students. There we go. Now we can see it. So today I was going to go through questions 1 to 9. And as I was going through and just doing the questions myself, I realized question number 9 is sort of at the crossover point between this first section and the next part of this. So you may have had some sort of difficulties perhaps thinking about it. That's okay. We'll talk about it today. All right. So number 1, a pendulum swings back and forth. So, oh, that's what I forgot. And need to get this set up. There we go. So we got a pendulum. And the pendulum swings back and forth 20 times in 15 seconds. So we're talking goes from here to here and back. And that represents one cycle. And so it does that, this is question number 1, 20 times, and it takes 15 seconds to do that. So if we go 20 times divided by 15, we're going to come up with 1.5. Well, what is that? Well, times per something per second, that's a frequency. So we could say this is cycles per second, times per second, swings per second. That's going to be hertz. Now for the period, well, we could take, the period is the time for one swing. So we can take our 15 seconds and divide that by our 20 swings, and that comes out to be 0.75 seconds. That's the time for one swing. Now, state that, but then I want you to remember that we define period as being 1 over the frequency, and the frequency as being 1 over the period. It's an inverse relationship to these. So we can take 1 over our 1.5 hertz, and that's equal to 0.75 seconds. So you don't have to set it up from the initial values that you got. You can use this relationship to recognize those two. All right, number 2, a swimmer notices 30 waves. It's supposed to be 30 waves. Striking a breakwater in 1 minute. They want to know what the period is in seconds. All right, so 1 minute, that's equal to 60 seconds. And a period is a measure of time. And so we're going to have our 60 seconds on top and our 30 waves down below. And 60 divided by 30 is equal to 2.0 seconds. Question number 3. Determine the frequency of each of the following. A basketball player scores 36 points in 24 minutes. So we're talking frequency, and frequency is cycles, things per time. Okay, that's our definition. So in this case, we're going to take our 36 points, divide that by our 24 minutes, and we can leave it in minutes. And so then what we get is 1.5 points per minute. And that's perfectly acceptable as a frequency. That's supposed to be B. A roadrunner who escaped coyote 27 times in 9 minutes. So a frequency, 27 escapes in 9 minutes. And that's equal then to 3 escapes per minute. Did you ever watch Bugs Bunny Roadrunner when you were growing up? I realize you're all mature and grown up. All right, a fan turns 170 times in 15 seconds. So we have 170 rotations in 15 seconds. Do that to math. And we get 11.3 turns or rotations per second. Right, question number 4. Question number 4, determine the period of each of the following. So here we're determining the period, and period is always measured in time, in seconds, or potentially in minutes. So when we're doing this, so in A, we have 30 times in 12 seconds. We're going to make sure that 12 seconds are on top and 30 times, 30 beats are on the bottom. So we go 12 divided by 30, that's equal to 0.4 seconds. That's how long a beat is. For B, it takes 8 seconds, so the time goes on top, 2048 vibrations on the bottom. And we do that, and we get a value of 3.9 times 10 to the negative 3 seconds. Finally, we come to C, the moon, which travels around the Earth 6 times in 163.8 days. We're going to take our 163.8 days, divide that by the 6 rotations, and then that works out to be 27.3 days. So you can think of this as the time between full moons. That's pretty close to 28 days, which is equal to 4 weeks, which is approximately 1 month. So how many full moons would we have a month? Generally, 1 full moon per month. Can we have a full moon, 2 full moons in a month? Yep. And that second full moon, anyone know what it's called? Tim? Kaylee? Ava? Haley? Yes, Haley. You're right. It's a blue moon. All right, let's continue on. Number 5. Calculate the frequency of each of all these periods. All right, so we're wanting to calculate frequency, and the relationship between frequency and period is 1 over the period. So for A, we're going to have 1 over 5 seconds. That's equal to 0.20 hertz. B, we're going to have 1 over 0.01 seconds, and so that would be equal to 100 hertz. C, we're going to have 1 over 2.5 times 10 to the negative 2 seconds, and that is equal to 40 hertz. Suddenly I'm doubting myself and it's checking, and we're talking, yep, 40 hertz. Oh, that's correct. So that brings us to D, and D, so we're going to have 1 over 0.8 seconds, and that is equal to 12.5 hertz. E, we're going to have 1 over 6 seconds, and that's equal to 0.167 or 1.7 hertz. And finally F, 0.40, 1 over 0.40 minutes. And so that gets us a value of 2.5 cycles per minute. So what we can do, but that's not hertz, we can go 1 over 0.4 times 60, and when we do that, we get a 4.2 times 10 to the negative 2 hertz. And that's how the answer is keyed. All right, question number 6. Number 6 is calculate the period. And so period is 1 over the frequency. So we're always going to take 1 over 10 hertz. So that'd be 0.10 seconds. B, 1 over 0.25 hertz, and that's equal to 4 seconds. C, 1 over 500 kilohertz. Kilohertz is 500,000 hertz. That's a lot of hertz. Oh, sorry. 2.0 times 10 to the negative 6 seconds. That's the time for one of those hertz. CDD, 0.10 hertz, and this is doing 1 over that, and that would equal 10 seconds. E, 1 over 2.5 hertz, and that's equal to 0.40 seconds. And finally, F, 1 over 3.5 hertz, and that is equal to 0.28. Oh, come on, just do it right. 0.28 seconds. All right, continuing on, question number 7. The horizontal distance between the endpoints of a swing of a pendulum is 8 centimeters. What is the amplitude? All right, so let's do some discussion. So we're saying we have this pendulum that's swinging back and forth, and they're saying this distance here is 8 centimeters. All right, so let's consider the motion of the pendulum. So the time, the one period of the pendulum is for the pendulum to start here, goes all the way across, and then comes all the way back. That is one cycle. Or if we considered, starting at this point, then the pendulum's going to swing up to here, come down, swing across over to here, come down and swing over to here. That would be one cycle. Like, you don't have to start at one end. You can consider it starting through here. So that would be one cycle. So what they're telling us is this is 8 centimeters. Now, if we consider a wave, because they're talking amplitude, a wave goes out, comes back, goes out, comes back. So here we have the center point, the rest point. And we're saying that this is equal to the amplitude. But what this tells us is that this from here to here is 8 centimeters. So how much is the amplitude? 4 centimeters. So a little bit subtle on that one. I just thought it'd be good to go through this discussion here. Question number 8, a tuning fork. If you play guitar, you might have used a tuning fork. You've seen them. We've got them in class, and you may have used them. So a tuning fork is just a piece of metal like this, and it has a handle here. And the point is that when you strike these, bang, these are vibrating back and forth, and they continue vibrating back and forth really nicely, and they give off a sound of a certain frequency. So we're told the frequency is equal to 200 hertz, which means the way the tuning fork goes back and forth 200 times every second. We're told that the amplitude of the tuning, the amplitude is 0.13 seconds. Okay, so just again to refresh, here's our wave. Amplitude is here, and that's 0.13 centimeters. So how far does the end in 1 vibration? How far does the end of the tuning fork go? Well, it's going to go at 0.13, it's going to come back 0.13, it's going to come down 0.13, and it's going to go up 0.13. There's 1, 2, 3, 4 times a 0.13, and that's equal to a 0.52 centimeters. That's how far it goes in one vibration. So how far does it actually travel? Well, it's going to go 0.52 in every vibration. It's going to do that 200 times a second, but it's going to do it for 60 seconds. So if we go 0.52 times 200 times 60. I did that wrong. 0.52 times 200 times 60. We get a value of 6240 centimeters. And I think that book talks about it as being or the answer key talks about it as being 6.2 meters. So every minute, that's how far it goes back and forth. So, reminder, so we think of a tuning fork arm as going one, out, and back to here. 0.13, 0.13, 0.13, and 0.13. And that's where we come up with our 0.52. All right, that was question number 8. Oh, we're going quicker on this than I thought. Question number 9. So we've got, they give you the wave, then it goes up, comes down, goes up, comes down, goes up, and comes down. And this is A, and this is C. And by measuring, find the wavelength. So the wavelength would be from here to here, or from here to here, or from here to here. Doesn't really matter which one you measure. They're all going to come out to be 3.5 centimeters. So we can say the wavelength, 3.5 centimeters. And then it says the amplitude. And so we measure the amplitude from here to here, or from here to here is the amplitude. And measure the amplitude, and it's 1.0 centimeters. Now B. This was A. This is now B. And it says B1, what is the speed of the wave? So from A to C is equal to 7.5 centimeters. The time for that, we're told, is 2 seconds. So that means our velocity is equal to 7 seconds, because it's 3.5 centimeters per second. That's our velocity. And then they said, well, what's the frequency of the wave? And the frequency is equal to 1 hertz. And the source frequency would also be equal to 1.0 hertz. Well, where do you get that from? Well, the distance, we have a velocity of 3.5 centimeters per second. We have a distance of 3.5 centimeters. And so if we take our 3.5 centimeters and divide it by our 3.5 centimeters per second, we come up with 1.0 seconds. That's not what we want, though, which is but I mean, it's still equal to the period, the frequency of 1 hertz as well. Okay, I'm just going to point out here, there's a what we call the universal wave equation. V is equal to lambda f. Velocity is equal to our wavelength times our frequency. And so if we use this, this is what we're getting onto next, maybe tomorrow. So our velocity is 3.5 centimeters per second. Our wavelength is equal to 3.5 centimeters. So our frequency, we divide this through, and our frequency then becomes 1 cycle per second. That's equal to 1 hertz. All right. So new lesson tomorrow. Hey, hope you have a great day, And thanks for tuning in, I guess. Bye-bye.